All right. So the assignment I've just given you will be due next Tuesday, and then the following Tuesday you'll submit stage 2 of the project assignments. And I have the description of that here in my hot little hands. I'll be passing back the description. My hands are hot because it's fresh off the copy machine. I reviewed the surface data that you gathered, and it looked good. I didn't see any obvious gaps in the data that you gathered compared to what you're going to need. And so the next phase of the project is going to be to take a look at GIS data and import it into Google Earth Pro so that you can get a sense for what the pipe diameters are, the slopes where they're known, the invert elevations, the catch basin data. And so basically explore the GIS data, then go into the field and verify what you can verify, specifically like the location of catch basins, the location of manholes. You won't be able to verify elevations of things or slopes necessarily. And then make a list of what you need to know so that I can provide that to Huntington Sanitary Board. Last year they were able to provide some old construction drawings that showed the slope of pipes where it wasn't in the GIS database. These old construction drawings were able to characterize the slope of the pipe and the material in a couple of the cases where we didn't know what kind of a pipe it was. And so there's some additional data that we can go and get if you know what you need. Now, this phase of the project, you are going to work either individually or with one partner. So it won't be the same groups that you were working in for the surface characterization. You had to sort of split up the area because there were so many individual lots, but now there are fewer pieces that you're going to be focusing on. There's just, I don't know, probably a dozen, maybe 20 pipes and the associated junctions that go along with that. So you've got 2 weeks to sort of start dissecting the data, and I thought what I'd show you to begin with is how to open up the GIS files using Google Earth Pro. Let's see if Google Earth Pro is still working on. No, so I'm going to remote into my computer to do that. Okay, so open up Google Earth Pro, and what we're going to be opening are shape files. And I emailed you the files yesterday, and they're also loaded onto MU Online. And what you'll do is simply zoom in on the project area. And this is important that you don't have all of Huntington showing. Otherwise, it's going to bring in the entire big shape file. Let me turn off the one that I already have imported. If I can find it. There we go. So I'm just going to zoom in on the area in question. All right, and then you go to File, Import, and you browse to the location where you unzipped that zip file. So when you unzip it, it won't show anything initially because if you look at the file types, it's looking for text files or CSV files. So if you change it to all files, then, or more specifically Esri shape, but all files is fine. What we're going to be importing are these SHP files, and that means a shape file. So if I do just Esri shape, you see that there are only 2 files that can be imported, the pipes and the points. So I click all pipes, and it'll give you a little warning here that you've got more than 2,500 features, and that's because this is the database for the entire city. And so we don't want to import the entire city all at once because that'll degrade performance. We'll just restrict to view, which means it'll import those elements that are in the area that's currently on screen. So if I click in restrict to view, then it gets 703. I don't want a style template. That's not what we think it would be. So if you can see that it's hard to even see anything that's there because the pipes aren't turned on yet. Turn on the pipes, then there are these little lines that are showing up, but they're hard to visualize, so we'll change the color of them. I don't know if it imported them or not. Let's try that again. I'm going to delete that. Well, a little. Not as much as I wish it would. Alright, but that's a good suggestion. Okay, we'll do File, Import, Pipes. Just restrict the view. Alright. Don't want a style template. It's not showing them. Well, this worked great yesterday. And here's the proof, is that you turn on the pipes, and what it initially has is pipes that are very faint white, and so if you change the properties when it imports, then you can change the color from white to like a bright red and increase the width. I may have so many of these different elements open that that's why I'm not able to do it on again. But that's the process you go through. File. Well, I'll try again with the points rather than the pipes. Import points, and I'll just restrict a view. Okay, points. There we go. Okay, so there's some points, and you notice that when you click on one of them, it pulls up some information. So that says it knows the catch. It's a catch basin. Has a top elevation specified. If you click on a pipe, it's got the elevation in, elevation out, VCP, vitrified clay pipe. So that's a pretty old one, 12-inch diameter. So combined sewer here, but you'll notice that there's no elevation in or elevation out. So if that's the pipe that we're interested in for the project area, then that's some missing information that we'd either have to gather based on the elevation of the upstream pipe, or maybe asking Huntington Sanitary Board if they have the construction drawings for that pipeline. It means solidified. For example, another time where you see the word vitrified is in hazardous waste management. Like if there's a gasoline spill into soil, they'll put in 2 big electrodes and they'll just electrify the soil until it melts. And they call that in situ vitrification. And so it means like, well, the soil melts. And so it's like you're turning it into glass, basically. Yeah. So vitrified just means solidified. It's a clay pipe, but it's not like mushy. You know, it's hardened clay pipe. All right, so any questions about how to import the shapefile? I don't think you'll have any problems. I think it's just that I've imported this so many times that it's on top of itself. File, import, all pipes. I've already read it in, but all right. So that's how you get at the GIS data. So a week from today will be the next homework assignment. 2 weeks from today will be stage 2 of the project. The entire project area, yeah. All right. So you'll need to go out into the field to take a look and see if, you know, the map says there's a catch basin somewhere. Is there really a catch basin? And maybe make note of if it's full of sediment. You know, is water actually going to get into that catch basin? And remember that part of what we're doing in this project is making a list of suggestions to Huntington Sanitary Board. And so if there's a catch basin that needs maintenance, then that's something that they'd probably appreciate hearing. But at the same time, if it's clogged, then you need to model the fact that it's not going to be accepting surface water flows during the analysis phase. So maybe unclogging that pipe is going to make the sewer even more crowded than it was before during a wet weather event. The GIS maps? No, I wouldn't say that they're able to update it yearly. In fact, they don't have GIS mapping in a lot of the city. So they're certainly not going every year to verify what they've got in the map. Okay, well, what we're going to start off with today to introduce the idea of basic hydrological principles, because so far we've been doing a lot of urban hydrology and we jumped into that without some of the basic background information. And so we're going to watch a video called Hope in a Changing Climate. It's about 30 minutes long. It's something that I heard about when I heard an interview with the main author of the script for the movie. So we're going to watch that, and then we're going to jump back to some basic hydrology principles. Can you think of any place close to home that the environment has been degraded and where restoration is needed or is sometimes already being applied? Mountaintops, yeah. Whenever the mining companies remove a mountaintop, they are required by law to have a certain level of restoration, and I don't know that it's to the same degree of the transformation that we saw here, but at the very least they throw some grass seed on top of the rocks and say that it's restored. So it's interesting to see what can happen when it's done right, with the terracing. And the main reason I showed you that film was to introduce the ideas that hydrology has an impact on human society in a really major way. That it can affect agricultural productivity, it can affect where people are able to live, their standard of living. In China, the communities that experienced restoration, I think it mentioned in the film that their income tripled, the average incomes, because they were able to move from just goat herding into higher return agricultural crops. And so hydrology matters. And the other aspect of it, besides just emphasizing that, is I think that shows really dramatically the principles of infiltration, precipitation, and that's the purpose of today's lecture, is just to introduce basically an overview of hydrology and talk about the overview of where we're headed conceptually for the next part of the course. So here are some images that show flooding in the United States. That's a result largely of urbanization. And it shows the impact of when people are forced to build in areas that are low-lying. And for a lot of West Virginia, people will put in their homes or businesses very close to a creek that when flash floods occur, that's where the water happens to go, is in the flat, low-lying areas that are easier to build on. And so it has a big impact on the quality of life in our state. It's all over the world that hydrology is important, and this is an image of a channel in the United Arab Emirates where I used to live, and you can see from the hillside there that there's essentially no vegetation on the mountains, and as a result of that, when it rains, the water concentrates very rapidly and it flows through this channel directly into the sea. They simply don't have the capacity to capture all of the water. And they have a few groundwater recharge dams that have been built to try and capture rainwater when it does rain over there. And usually their 4 inches of rain per year will happen in just a couple of days. But the vast majority of it just flows directly into the sea. So I like this diagram because it's an overview of the hydrologic process, and there's a slide very much like it on the next screen that just presents things a little bit differently. But let's look at the big picture of where water resources engineering, what it includes, and what we're going to be focusing on for the rest of the course. So in fluid mechanics, you were introduced to the principles of pipe flow. And so pipe flow includes things like the no-slip condition and characterizations of boundary shear stress. And then we went into empirical methods for estimating what flow rates through pipes will be when you have a pressure difference, like the Hayes and Williams equation, Manning's equation. But in hydraulic engineering, we moved on to open channel flow and calculating water surface profiles and gradually varying flow, rapidly varying flow. And now in hydrology this semester, we're going to be focusing predominantly on surface flow. There's a whole other sequence of courses that focus on the movement of water underground. And we'll touch on just a couple of well equations at the end of the semester that would allow you to calculate the yield of an underground well that's pumping water to the surface. But there's a lot more to it than that. And so what we're really going to be focusing on of these three sub-areas of water resources engineering, we're going to be focusing on surface hydrology for the majority of it. Now, this shows the water cycle. And the main thing to keep in mind is that energy is driving the water cycle. Sunshine that is intercepted by the ocean and water on the land surface is driving the movement of water because of evaporation, which occurs from the ocean, and evaporation also occurs from surface waters that are inland. But the evaporation that occurs leads to condensation. The condensation is transported over the land, and precipitation can fall directly onto the surface. There's also precipitation that goes into the ocean. And there's an image that we'll take a look at a few slides from now that illustrates the relative fraction of how much rainfall is onto the surface versus how much rainfall goes directly onto the ocean. Obviously, if it's raining into the ocean, then that's not usable fresh water that we can capture or make use of or enjoy. But it's energy that's moving the water from the liquid phase into the vapor phase and then over the Earth's surface. Now, where the water goes from here, it falls onto the land surface in a variety of different forms. There's rain, snow, ice. That water is trapped in mountains and glaciers. When it begins to run off, it can infiltrate into the soil. And when infiltration gets into the soil, it can just be bound to the soil. So soil moisture is water that is essentially stuck in the soil, and it's not going to be moving. But when water does move through the soil, then that's the process that's called percolation. Water can come out of the soil in a couple of different places. The next slide shows that a little bit in more detail, that water can go directly into the ocean through underground, or it can emerge at the surface as fresh water and then move over the surface towards the ocean. Water is also lost through plants themselves, and the process that's listed here of evapotranspiration is both evaporation of free water and the transpiration of water, essentially plants breathing, which their breathing includes a loss of moisture that they then replenish through their roots, which is taking water out of the ground. So that water cycle is very important, and here's a USGS provided slide that illustrates a few things a little bit differently. And what I like about this slide is that it goes into detail about where groundwater flow comes out of the surface. And so there can be seepage, where it just seeps out of the ground surface as a trickle. It can pool in a spring where there's actually a puddle that's there and is discharging water in kind of appreciable amounts that could be tapped for, there are a lot of bottled water companies that try and tap into springs when they're known. Groundwater can contribute to fresh water, and that's called base flow, when groundwater that is essentially precipitation that infiltrated into the soil emerges out of the soil and gets into a river or a lake. That's known as base flow. But there again, water can also come from rivers and lakes back into the ground, and so recharging the ground and essentially go back down, back to the ocean. So the water cycle is driven at different speeds at different places in the earth, and it's very slow at the poles because the temperatures are low, and it's very high at the equator because temperatures are higher, and that moves the water from the liquid phase to the vapor phase a lot more quickly. So in some places it's very wet, in some places it's very dry, but hydrology is important in all of these areas because when it rains, even just very briefly, it can have a huge impact on the land surface. And these are some pictures that I took when I was living in the UAE. And this is one of the groundwater recharge reservoirs that they've built in order to try and capture precipitation and get it to go underground. And it'll never be as lush as some of those images from China or Ethiopia that we saw, just simply because you can't grow plants on rocks necessarily. At least they had soil in those other places. But here, a lot of the countryside is just rocks. But when it rains in the urban areas, parking lots which are just sand and not having a stormwater collection network in a lot of the third world leads to flooding, and people's cars get completely submerged, and it causes a lot of damage. You can see the effects of that. This is just you know, an ordinary city block that the parking lot is a little bit low-lying and didn't happen to have any kind of drainage network, so a lot of ruined cars. And you can see that they're trying to keep this car nice. They've got plastic on the seats still, but there's probably water in the engine compartment, so the plastic on the seats isn't going to make much of a difference at this point. This is a picture I took as I was driving down the road. I shouldn't be taking pictures as I drive, but I was, and I got a taxi, and it looks almost like a water taxi, but it was just, you know, people need to move around, and when the streets are flooded, they continue to drive. And this fellow's strategy for keeping dry was a plastic bag over his head. I don't know how far he made it before he collapsed, you know, suffocated himself. But he was nice and dry when he collapsed. Since they don't have stormwater networks in most of the UAE, their strategy for dealing with excess ponding is to pump it out using trucks that normally carry sewage. A lot of the UAE, instead of having a sewer network, people will have basically like a septic tank without leach lines. They'll just have a big storage tank for all of their wastewater, and then trucks have to come and pump it out every couple of weeks. Whereas with a septic tank, you only have a septic tank pumped out maybe every 3-5 years, because the majority of the water is leaching into the soil after it degrades in the septic tank for a couple of days. But in the UAE, they're just storage tanks. And so they have these trucks that normally would be used to pump sewage water out of people's homes, but when it's really rainy, they'll go to a flooded intersection and they'll pump the rainwater into the truck and then drive off to the desert and discharge that water into the desert. Well, this truck was on the side of the road and it got hit by another truck, and so it was just completely obliterated when I took the picture of it. This is showing several days after a storm how water is still accumulating on the in the curb area, and this is dangerous for people to be driving several days after it's wet in most of the town. People are sort of out of the mindset that the flooding is gone. And at night, if you were to come around a corner and drive, you know from experience that when you have two wheels in the water and two wheels not in the water, it can sort of pull the vehicle in towards the curb. And so that's a dangerous condition that causes a lot of accidents. This is showing more ponding. This is an intersection that was close to where I lived, and these are brand new interchanges that are, you can see it's still just under construction. This is an old construction that doesn't have a drainage network because back then they didn't think of it. It's just illustrating that even now people fail to consider the effect of precipitation and the effect of hydrology on infrastructure. So it's ponding here. This will be a dangerous intersection for the foreseeable future because they didn't put any kind of a collection network in there. This was on the university campus that I lived at, and it's hard to tell, but the depth here it was up to my son's waist. We went for a walk when he was small, and he went for a little swim in the rainwater there. So it was pretty deep. I mean, probably coming up on 2 feet deep. And so it was hard to get around campus as wet as it was. Over there, this is some of the academic buildings, and they have these big walkways that are made out of granite, and it's really slippery when it rains over there. I mean, it's slippery even when it's not raining, but when it is raining on polished granite, it's hard to stay upright. It's almost like ice skating, walking from place to place over there. So, a couple of interesting pictures showing when it rains other places. I mean, I should take some pictures of when it rains here on campus, because we have flooding along the road there, and I think I was in the engineering building one time, and it was like a spectator sport. We were watching people step into the gigantic puddles because there was no way around them, and getting their ankles completely submerged in the water. I already referred to this, and it shows the relative quantities of precipitation. And you can see that for every 424 units of evaporation, that it takes 424 units of evaporation from the ocean in order to have 100 units of precipitation on the land. So for every 1 unit of precipitation on the land, there's approximately 4 units of precipitation onto the ocean. And that's simply a function of the relative surface area of land versus ocean. And so it rains more onto the ocean than it does onto the land. But what's interesting to look at is that there's a lot of evaporation from surface water, from channels, from dams and reservoirs, but eventually all of the water makes its way back into the ocean, whether it's through evaporation and the moisture will get back towards the ocean, or it can be the groundwater flow into the sea. Here is a interesting figure that shows the relative distribution of where is the water on the Earth. And the vast majority of water on planet Earth is in the oceans. And so ocean water, because it's saline, isn't directly usable by people. We have to desalinate it in order to be able to use it. And either artificially with really energy-intensive processes like thermal distillation or reverse osmosis, it's incredibly expensive, or naturally just by allowing evaporation to have moisture escape and leave the salts behind. But you can see of all the water on Earth, only 2.5% of the water is fresh. The rest of it is salty ocean water, saline groundwater, meaning water that's underground but close enough to the coastline that that seawater has intruded into the groundwater, so it's not really usable. And then saline lakes like the Salton Sea in California, the Great Salt Lake in Utah, and so on. So a small fraction of fresh water on planet Earth, and most of it is in places where it's very difficult for us to use. 2/3 of the fresh water on planet Earth is in glaciers and ice caps, and those aren't very easy resources, although I did hear some far-fetched idea to bring an iceberg to New York Harbor. If there was ever a water shortage there, they could like tow an iceberg towards the East Coast. And there was, I think, a vodka company that was thinking about also getting an iceberg and using that for the production of their vodka, just so that they could be a little bit different, you know. But surface water, so think about the Ohio River. That's where we get our water from. The Ohio River is 1.3% of 2.5% of the total quantity on Earth. And so the fact that we have such abundance next to Huntington is really a rarity, because most of the water is in the ocean, and most of the fresh water is either underground or trapped in glaciers and ice caps. And so most of the surface water, if you break that down, much of that is just ice and snow. That's not necessarily in a glacier or an ice cap, but is maybe at the high northern or the very low southern latitudes. A small fraction of it is in lakes, but rivers, 0.46%. So a very, very tiny fraction of the fresh water is actually as rivers. And so we should feel fortunate that we have such abundance of water, considering where most of the water is on the planet. One of the important concepts that's introduced by Chapter 2 in your book is the idea of a watershed. And a drainage basin, or sometimes called a catchment or a watershed, is an area that collects precipitation and discharges it to a single outlet. And you can see that there's this dashed line that's indicating a drainage divide. And it's essentially the highest part of the hill. It's the ridge line of the hill. So if you trace the ridge line, then a drop of water that falls on this side of the line is going to flow to some other watershed outlet. But a raindrop that falls on this side of the line is going to flow over the surface and then eventually get in a stream, flow through the stream, and then comes to an outlet. And an outlet is a concept that I struggled with when I was first learning hydrology because it's an arbitrary location. We can just point the finger here and say, this is the outlet. And then there is a watershed that's upstream of that point. An outlet is any location of interest that you want to identify, and then you can have an upstream area that contributes to that outlet. And so there's nothing special about this point or this one or this one. It may be that there's a road going over this river here. So we're using this watershed corresponding to this outlet because there's some feature of interest that we have to design around the flow rates. We're going to take a look using Google Earth at a watershed, and you have on your homework assignment a brief exercise where you need to delineate a watershed using Google Earth. And I think I can still do, no, I can't use the area tool, so I'm going to remote back into my computer again, because the Pro isn't enabled on this computer any longer. I need to type that serial back in. Alright, so in your assignment it says to go to a certain point in Lesage, which is out here, and so if you push down on your center mouse button, that allows you to tilt, and then you can look at things in 3D. And so if we wanted to try and find a watershed, it looks like here's a good watershed. There's some high points there. As you tilt, you can sort of get an idea that there's a ridge line. And so we could trace that ridge line using the tool that is not polygon, there's a pathline tool. Yeah, we could, with the pathline tool, try and draw where we saw that ridge line as we were panning around. And then that path will be visible as we, oh, I shouldn't have closed that. You'll do better than me. You'll learn from my mistakes. The other thing in the homework assignment, I suggest that you use this polygon tool, because what you can do is you can draw an area, draw that ridge line, and then under measurement it will tell you the area in acres. And so this is 60 acres for this little watershed here. I could turn that off, or I could turn it on and see if the points are in the right place. Maybe edit the points if necessary. So the watershed, any raindrop that falls on this side of the hill is going to flow somewhere else. But any raindrop that falls within this catchment is going to flow towards the outlet that's right here. We'd have to look and see where's the lowest elevation. Okay, so this is elevation 700, so probably the stream is right in here. This is the low point. And then you can see there's a stream running along the road there. So the water from all of this area makes its way into the stream there. Later in the semester we'll take a brief look at a computer program that automatically looks at the elevation data. The reason why the map is all three-dimensional like this is that there are these things called digital elevation models, and it is a point-by-point grid that says the elevation, and they have just an aerial photo that's flat, but then they exaggerate the aerial photo based on the known DEM, and the elevations that it says down here at the bottom of the screen are also based on the DEM. So towards the end of the semester, there's a program that automatically analyzes the DEM data, and it will draw the ridgeline for you and calculate the watershed area. And that's a really nice hydrology program. It's called WMS. We'll be getting to it later. A nested hierarchy is because you can pick a watershed area, you can pick an outlet at any location, and so a nested hierarchy is the idea that small watersheds are found within larger watersheds. And how much runoff you see from at an outlet is partly due to the size of the watershed, but it's also due to other factors like the land use that is being applied in the watershed, the types of soils that you have, whether they're maybe a sandy or gravelly soils versus clay soils, which don't allow as much infiltration. Also, the conditions of the terrain based on the slope and the shape of a reservoir. It's very long and narrow versus if it's more circular, that can have an impact on the runoff quantity and the peak flow rates that you see. And of course, precipitation amounts and duration also have a huge impact as well. We'll be learning how to characterize each of these parameters and then models that say how much flow rate Q you'll get for a certain watershed. And that the direction we're headed in is trying to estimate Q so that that could be handed off to the hydraulic engineer to design a culvert or design a bridge or whatever feature or channel to accommodate the flow. This is the Mississippi River Basin, and the next series of slides is to illustrate the idea of a nested hierarchy. And you can see the United States in general, the Mississippi River drains this much of the United States. And to the west of that, the Rocky Mountains, it all flows towards the Colorado River, much of it. You know, up north it's other rivers, but you know, Utah, Colorado, Arizona, Nevada, California, towards the Colorado River. To the east, there's like the Potomac Highlands and stuff, but all of this area is drained by the Mississippi River. In the next series of slides, we're going to be zooming in on a certain location and then looking at what's upstream of that location. So if we just select this branch of the Illinois River and exclude all of the area that's not contributing to that. So we can zoom in on just one subset of the dendritic network. I mean, this dendritic network goes all the way to Colorado. And this is one of the things that actually, I need to bring in a little reading assignment for you. It's a 2-page article that talks about one of the reasons why America has such strength is because of this river network, which lies on top of a very productive agricultural region. If you look, the majority of the United States growing areas can be reached by river barge, and it makes it very cheap to transport agricultural products to markets all over the world. But if we just zoom in, then this is the upper Mississippi River Basin. You can see the Illinois River and just the streams that are within that outlet that we specified. And so now if we pick a more specific section of the Illinois River and exclude all of those watershed sections that are outside of that network, then here's the Illinois River Basin. And the watershed areas are getting successively smaller. Now we're down on the scale of 20,000 square miles. And just going in on one section of that watershed, the Sangamon River. And so this is just a tiny section within Illinois, the Lake Decatur watershed, 925 square miles, and that's still a huge watershed. Don't get me wrong. I mean, we've gone from 20,000 square miles to 900 square miles. It seems small, but it's still. If you tried to model this in the computer using a DEM, it would take a really long time. But you can even zoom in on a small section of that Lake Decatur watershed and get into the Friends Creek watershed. So you'll get a chance to do that, to pick an area in the state of West Virginia and create a watershed model for it and try and understand the relationship between precipitation and runoff for the area that you're interested in. You'll be able to pick maybe someplace close to your house, or a state park that you like, or maybe a recreational area that you've been to before. The text makes the point that all of the models that we use in hydrology are derived from several basic laws, and the most important among them is the conservation of mass. That is something that we've relied on a lot for sizing of reservoirs, sizing of ponds, just the idea that a change in storage is in minus out. Mass is neither created nor destroyed, so if we keep track of where the mass is, then we can find out a change in storage required to contain it. Three other really important basic laws that are applied to hydrology: Newton's laws of motion, which we're all acquainted with from our time in statics and dynamics. The laws of thermodynamics are important, especially when we get into the section of the course that deals with evaporation, because the evaporation of water is governed by two main processes. One, how much energy the water absorbs, and the second part is transport, which is the movement of the moist air that's right close to the surface of the water, so that additional evaporation can occur. So thermodynamics goes into, in terms of hydrology, is very important for understanding the evaporation rate, not only of free surfaces of liquid, but also evapotranspiration, where we're characterizing evaporation from plants. And then Fick's first law of diffusion is that substances move from areas of high concentration towards low concentration. And that helps to explain phenomena like wind and the movement of humid air. And so what we'll be getting into in class on Thursday is more about the global climate and some of the phenomena that move moisture all over the planet, and we'll discuss more about the big question of the course. This takes a few minutes to get through this slide, and we're out of time for now. Let's just jump back to a couple of announcements before we finish for today. Take a look at homework 4, due on Tuesday, project stage 2 the following Tuesday. I have the quiz key here. If you'd like to take a look at the quiz, it seems like the two most common mistakes was on the second problem. I gave you the surface flow velocity of 8 feet per second. And so what I was hoping you'd do is think about how long it would take for a particle to travel over the parking lot. And so calculate the time of concentration and use that. Not just assume a duration, but use the 600 by 300, and any distance would be okay. Most people came up with the longest flow distance and then the velocity to find the time of concentration. If you want to take a look at that, you can. The other issue that came up a lot is on question 3, the two main impacts of urbanization on runoff is that the flow rate, the peak flow rates get higher, and they are also sooner. And so it's the shift of what the hydrograph looks like, the before urbanization and after urbanization. So I'll leave that out if anybody wants to look it over, but I know that we're out of time, so I'll see you on Thursday.